Dear Level 3 students, Credit Hour System, Department of Socio-Computing at the Faculty of Economics and Political Science, Cairo University. Welcome back to our course named Social Network Analysis. Lecture 9. Let's start with a brief review of what the previous lectures covered. In the previous lectures, in lecture 1, we discussed the concept of complex systems, and I know you studied this in the first year, but we revised the concept of complex system. And then in lecture 2, we studied complexity of social phenomena. And in lecture 3, we started by the definition of social network, and this is why we studied complexity and complex system, because social network is one way of modeling complexity of social phenomena in order to understand the complexity of social phenomena. And also social network analysis is one methodology that can be used in order to study complex systems. So these are covered in the three first lectures. And then in lecture 4, we discussed some of the general network properties. We discussed the properties including network size, the directed and undirected networks, and network representation. And we say that we can represent network in three different ways. We discussed the adjacency matrix, the linked list, and the adjacent list. In lecture 5, we continued to study the general network properties, and in lecture 5, we discussed concepts like network degree, and when discussing network degree, we discussed also the degree of the nodes inside this network and how we can calculate network degree from nodes degree. And then we discussed the concept of degree distribution, and I think you made an exercise with the teaching assistant at the sections in order to know how you can calculate degree distribution. And then in lecture 6, we discussed some properties of the edges of the network. We know that any network is composed of a set of nodes and set of edges. So in lecture 6, we started by studying the properties or the main properties of edges. In this context, we studied the difference between weighted and unweighted edges, and then this created to us several concepts like weighted and unweighted networks, and also we studied the concept of paths. In lecture 7, we studied some properties of nodes like the centrality measures, and centrality measures means some measures that tell me who is the most central node inside this network. And in the centrality measures, we studied degree centrality for undirected networks, and in degree and out degree centrality for directed networks. We also studied betweenness centrality, and then we studied eigenvector centrality. In lecture 8, which is the previous lecture, we studied other network attributes or properties. These include network connectedness, and then based on the network connectedness, we discussed the concept of components and how network can be decomposed into several components. And from components, we also studied the concept of giant components, closure rule, triadic closure, clustering coefficient, bridges, and loop bridges. So lecture 8 was one of the most dense lectures. I hope you like it, and we will proceed today in order to continue discussing some network properties. Today, in lecture 9, we will continue, as I said, we will continue discussing network properties through exploring the following concepts. We will explore the concept of strong and weak ties, passive engagement in real-world networks, nodes positioning, structural equivalence, and social implications of structural equivalence, structural holes, embeddedness, and social implications of embeddedness. Let's start with discussing the concept of strong and weak ties. Is there strong ties and weak ties in social networks? We will see. As you know, in real social systems, social ties that link people together can vary according to their strengths. In friendship network, for instance, the strength of friendship varies from one pair of friends to another. The same concept applies on trust networks and many other real social networks. In the terminology of social network analysis, we can say that links between nodes also can vary according to their strengths. For simplicity, we can differentiate between two types of links or ties, strong and weak. We call a link to be a strong tie if there is a strong relationship between the two nodes participating in this tie. Similarly, we call a link to be a weak tie if there is a weak relationship between the two nodes participating in this tie. And as we see in the figure, here in the slide, we have a social network with links, and on each link we find a letter S or W, S for strong and W for weak. And as an exercise, you may observe this figure and then get all the pairs of nodes with strong links or strong relationships and the pairs of nodes with weak ties or weak links or weak relationships. Do you remember the triadic closure we discussed in the previous lecture? We can now represent this triadic closure using the notation of strong and weak ties as follows. We can talk about strong triadic closure. What is a strong triadic closure? If a node A has links to node B and C, then B and C are likely to form a link, as you studied before. But if the link between A and B is strong, and the link between A and C is also a strong tie, then we can call the triadic closure between A and C a strong triadic closure. So this is the same concept of triadic closure that we have studied before, but now we can differentiate between strong triadic closure or regular triadic closure. However, if a node A, we can say that node A will violate the strong triadic closure if there exists a strong tie between A and B and a strong tie also between A and C, and no triadic closure is created between B and C. In this case, we say that node A will violate the strong triadic closure that we have discussed now. Now we will study the social implication or the social applications of the concept of strong and weak ties. Why do we study strong and weak ties? For sure, there is a social application for this concept, and for this reason we study strong and weak ties. In real social networks, one can see relationships with varying strength among people, as we discussed before. In an experiment about tie strength in Facebook, Marlowe and et al. Analyzed the friendship ties or links existing and reported in some users' profile. The results of this experiment showed that we have three categories of links that one can see in a user's friend list. These three categories are as follows. Number one, mutual communication, or number two, one-way communication, or number three, the passive engagement. So what do these three categories mean? We will discuss this now. The results of the experiment showed that maybe there is mutual communication between two friends. This occurs when the user sends a friend a message and the friend responds back by sending back a message to him or her. So the communication is mutual now. So this is the strongest tie or the strongest friendship link on Facebook. Another category of communication or links, another category of links in Facebook friendship is one-way communication, where the user sends a message to a friend and this friend may or may not reciprocate this message. So this category of communication or this category of link is not as strong as mutual communication. The third category of links observed in this experiment was the passive engagement. What is passive engagement? Passive engagement happens when the user follows the information about a friend without sending or receiving messages, but only following the news feed of this friend. So this is called passive engagement, and it is the weakest type or the weakest category of links observed in this experiment. Therefore, this experiment showed us that on Facebook, as an example of a social network site, there are three different levels of strength that could occur between two friends on Facebook. After discussing the strong and weak ties, we will now move on to another very important concept in social network, which is the node's positioning or the position of the node. While analyzing a social network, we can gain some insights from the positioning of a node within the structure of the overall network. Some nodes may be settled at the periphery of multiple components, while other nodes are located in the middle of a single component. The figure shown in this slide illustrates the node's positioning in a social network. As obvious from the figure, node B is located at the periphery of three connected components, and however, node A is located in the middle of a single component. Related to nodes positioning, there is a very important concept in social network analysis, which is structural equivalence. So we will now study what's the meaning of structural equivalence and what are the social implications or applications of structural equivalence in a social network. Position, as you know, usually describe structural correspondence or similarity. Actors who are connected to the network in the same way are said to be in equivalent positions. So we can define now the term structure equivalence. A structurally equivalent set of nodes is a set of nodes connected by the same relation to exactly the same people. In other words, these nodes have identical ego networks. So, if two nodes are structurally equivalent, means that they are similar both in the pattern of connection, which we call similarity, and they are also connected to the same nodes, which we call proximity. So, structurally equivalent nodes have the same network properties like centrality measures. Let's take an example on structural equivalence of certain nodes. In the figure that you see in this slide, I want you to look at this figure. The following figure illustrates how structural equivalence is about network location, and it also illustrates the difference between proximity and similarity that we mentioned in the previous slide. For example, points A, G, and M are similar in their patterns of connection, but they are not proximate, so they are not structurally equivalent. However, points A, B, C, D, and E, and F are all proximate. They are all connected to the same components, but they are not similar. They are not also structurally equivalent. However, points D and E are both proximate, both of them are connected to the same people, and also they are similar. Both of them have the same shape of relationships or the same shape of links. So, since D and E are both proximate and similar, we can say that D and E are structurally equivalent. Now let's discuss the social implications and social applications of structural equivalence. The literature in social network analysis shows us three examples of how the notion of node position and structural equivalence can be used in three different social applications. The first example is in status or role systems. The second example is to measure power in experimental exchange networks. And the third example is social homogeneity, and we will discuss these three examples in the following slides. Let's start with the first example, which is the role of structural equivalent in detecting the status or role systems. Network equivalences are seen as or can be seen as a formulation of status or role in a society. So, for example, as you see in the figure, a nurse is defined as a nurse by the characteristics of the relations that he or she holds with patients, doctors, and other nurses. The second example is power in experimental exchange networks. Power in this context is a function of the extent to which the actors rely on each other for the provision of some unnamed good, for example. Dependency here is a function of supply and demand, but supply here depends on the actor's position within the structure of the network. So, one must be connected to those who possess demand. Power in this context is best described under structural equivalence or isomorphism. Isomorphic actors are actors who have the same structural properties and thereby have the same power. So here, structural equivalence gives us an idea about the equivalence in power as well, because the structure reflects the power of the actor inside these special kinds of networks. The final example, or the third social application of structural equivalence, is social homogeneity. We expect actors belonging to cohesive subgroups to exhibit similar outcomes on different questions. A famous example is the Coleman, Katz, and Menzel study in 1953. They studied the adoption of the use of a new drug among physicians, and they noticed that homogeneous societies are societies which have cohesive subgroups, and both of them have the same manner in using this new drug. After discussing node positioning, which is the position of the node and the effect of the position of the node on its power inside the network, and we studied a relevant concept, which is the structural equivalence, because if two nodes are structurally equivalent, then they will have the same power and they will have the same measures of centrality and other properties of the nodes and networks. Now we will consider another related concept to the network positioning or the structure of the network. We will discuss structural holes. So what do we mean by structure holes? Assume now that we have a network of Facebook groups as in the figure that you see in this slide. So this figure represents a network of Facebook groups. We can observe that node P spans a structural hole of an empty space inside this network. The structural hole doesn't allow the cross interactions between separated components in the network. Node B here plays the role of gatekeeping. It regulates the access of both node C and node D to the highly knitted group to which B belongs. It also controls the information coming from C and D groups. So this position offers B an advantage relative to A, for example. This advantage lies in the following. First, B has an early access to information that originates in multiple non-interacting parts of the network. And second, B's position is at the interface between non-interacting parts, which gives him the opportunity for novel ideas. And third, B invests its energy between different groups instead of concentrating its effort or energy in the same group. This position, therefore, gives B a source of power in the organization or inside this network, and some studies emphasize that B position should prevent the construction of local bridges between these parts of networks or these components. In order to complete our speech regarding the structure of the network and how the positioning of certain nodes in certain places gives them power over or privileges over other nodes, we also have a related concept, but now it is not related to nodes, but it is related to edges or links, which is the embeddedness. In the figure that you see here in this slide, the local bridge between A and B has an embeddedness of 0. What's the meaning of embeddedness of 0? Local bridges has an embeddedness of 0 because it doesn't have any common neighbors from its endpoints. Now we will discuss the social implication of the concept of embeddedness. In social networks, individuals who are connected with an embedded link tend to trust one another more and have confidence of this integrity of transaction. Either this transaction is social, economic, political, or any other form of transaction. So the embedded link is very important because it is used to build the trust and confidence between people or between actors or nodes inside this social network. Now we came to the end of our 9th lecture, and I want to revise with you what are the main elements in which we talk or the lecture covered. We discussed the first element we discussed today is types of ties like strong and weak ties, and we say that we have different strengths of different relationships between people. So I'm not interested only in studying whether there is a relationship or not, but also I am interested in studying the strength of this relationship, and we differentiated between strong and weak ties based on this concept. And then we studied the social application of strengths and weak ties, and we studied passive engagement in real world network as an application of weak ties in social network websites or social network sites like Facebook. Then we moved to study the structure or the power of structure of the network and the power of the position of nodes inside this network. So we discussed the nodes positioning, and we discussed the peripheral position or the nodes with the peripheral position between many groups or linking many groups or many subgroups of this network. So these nodes may have privileges over other nodes based on their position inside the network, because they are linking 2 or 3 components that will be not related if these nodes are not existing or if they are absent. So node positioning is very important because the position of node may be one of the measures of its centrality or its importance or its power inside this social network. And based on node positioning, we moved to another very important concept, which is structural equivalence, and we discussed terms like structural equivalence and isomorphism, and we say that in order to satisfy structural equivalence, the 2 nodes must have both or exhibit both similarity and proximity, and we discussed the difference between similarity and proximity. Then we moved to the social applications of structural equivalence, and we studied 3 different examples of social applications that discuss the importance of structural equivalence of certain nodes. After this, we moved to the structural holes and see how some nodes spans structural holes, and these nodes, if they are absent, the network will be or will exhibit some structural holes, and this is point of weakness inside this social network. The final concept that we discussed today was embeddedness, and then we discussed also the social applications of embeddedness. I hope you enjoyed this lecture. For any further question or for more communication, please don't be hesitated to contact me on my email on the screen now. And you can also view these lectures on my YouTube channel or the YouTube channel of Cairo University as well. So waiting forward to hear from you soon. Thanks.